So good morning, and we are now starting our recording for this lecture on our class. And may I ask Althea Talion to open us with a word of prayer, so we can start.
Lord, we thank you for this day. Help us focus our minds and hearts on what we are about to learn. Bless us as we study and learn together. Keep us all safe. Amen.
Amen. Now, thank you, Althea, for opening us with a word of prayer. And just to run through with the attendance that we have, so I will call some names that I have not checked. Nikki Armada, are you around? Nikki is not yet there. Cindy Buendia, not there. Jika Junella, Ashlyn Duran, not there. We have Hakomile, Marie Beatriz Hakomile. Wala man. We have Labuson. We have Ledesma Liuk. Ari si Liuk gali. We have, who else? Franco is checked. No. Then we have Omar present and Tumlos. Yanson, are you there? Miss Yanson? Wala pa si Miss Yanson. Ryan Palabrica, not there. Miss Malio, Carmela, not there. Labuson, Hakomile, Duran. So we now proceed to our class lecture. So our topic for this day is about magnetism and electromagnetism. Now somehow electro refers to electricity. Magnetism is another concept, and we kind of combine them into a single term, electromagnetism, eventually. And later on we will see how related they are, how interconnected are these two terms. So if one of them exists, then the other will likewise exist. So we will show that in our later discussion. But again, this is the last chapter which we will include in our quarter exam. So this is chapter 6 or lesson 6. Now, a brief history of the idea of magnetism. So we run through with some important names. So we have William Gilbert. Maybe that family name Gilbert is also being considered as a unit of magnetism. So William Gilbert made some studies of the Earth, and he noticed that there's deflection when he has this compass, and he kind of relate that to the Earth, being probably the Earth being the natural magnet. So way back in the ancient days, we see also stones, and these stones that they found in one part of Asia Minor. So maybe in their time there's Asia Major, there's a major part of Asia, and then there's this minor part of Asia which is present-day Turkey. And in one part of that Asia Minor, where they walk, they step on a stone which we can probably call as a magnetite, or a lodestone. That this stone, naturally occurring, of course, since it's a stone, that it has an ability to move on its own and reorient itself, in a manner that will probably position itself along the magnetic field of the Earth. So with that, I think they were able to discover these magnetic stones. Now, other people, we have Hans Christian Ørsted. So Hans Christian Ørsted noticed that if you have a wiring that carries current, And if you put a compass needle or a compass beside it, no, a magnetic compass beside it, the needle of the compass, no, will behave, no, in a manner that as if it is being influenced by a magnet. No? Now, if you will try to examine the electric current, no, in the wire, no, is not magnetic. It's not a magnetic material. No? But somehow, a magnet, no, that is the equivalent of a compass, behaves, no, in the presence of an electric current as though it is influenced by another magnet. No? So this is the beginning of what they term as electromagnetism. No? So the relationship between current and magnetism, no, that are so intertwined. No? Now Ampere, we learn his name, no, from the unit of current. No? And maybe he studies a lot about parallel wires. No? What if two wires carries current, and if these wires, no, are producing magnetic field or magnetism, what will happen to the wire? Will the wire, no, stick together, or will they move away from one another? No? So what will happen to wires that carries current, no, and they are placed side by side? No? Now another guy, Michael Faraday. Michael Faraday, no, made a lot of concepts, no, in his Faraday's laws that he, no, probably, no, formulated our knowledge today of how to create a generator. No? So maybe, no, through his experiments, no, it led, no, to our present day, no, use of wirings, no, and magnets, no, in producing electricity, and we call those devices as generators. Generators or dynamo, no, the smaller version is called as a dynamo. And if this dynamo is being made to rotate, no, in a bicycle tire, no, you can actually let a bulb, no, glow or light up. No? So somehow, no, the movement there of the dynamo is producing the current that causes the bulb, no, of a bicycle, no, to light up. So again, no, those are concepts that probably, no, was conceptualized or given, no, into fruition by Michael Faraday. No? Then James Clerk Maxwell, we will run through with his name again, no? When we go to our second quarter. No? So towards the middle or towards the end of our second quarter, we will encounter his name again, no? Because he is the one that created this unifying principle in physics that combines, no, the idea of magnetism and electricity, and they put it together, no, together with light, and he unifies this principle, no, that these things are, no, actually, no, in one combined idea. No? So that's how advanced, no, is the thinking of Maxwell, and that's how revolutionary his idea. But look at him, no. He is when he I think, no, when he died he's very young, no, 1831 to 1879. No? So he died early, no, in his life. Now here's the naturally occurring stone, no, the lodestone. And of course, no, if you want to know, no, whether it really attracts things, you may need some iron, materials that contains iron or iron filings. No? So if you have some iron, no, and you cut it, no, using a hacksaw, or that's the that's the metal or the blade, no, of a saw that can cut through metals. No? Now the fine metals that are created, no, when you cut something, you can call it as sawdust, no, if it's wood. But if it's iron, no, or metal, then we call it as iron filings. No, so iron filings could be that small, or you can create them. No, and usually, you know, we use iron filings to visualize, no, the presence of magnetic lines of force. No, now magnetic lines of force are invisible to our eye. So for us to trace their path, then we need a metal, no, some powdered form of metals, no, to trace their path. No, so we will be able to see where they are actually moving. Are they released in some forms of lines or so on? So we can actually see that when we have these iron filings. When you pour little by little an iron filing in on top uh, of a surface that has a magnetic field. So if you make this very small, these lodestones, then you can probably have a compass. So I think in the olden days they use a lodestone, a small part of that lodestone, and put it in some leaf and make it float in water, so it can orient itself in some kind of a direction related or in line with the Earth's magnetic field. And you can actually know where is the north pole of the Earth with respect to that compass that improvised compass using a lodestone being placed on a piece of a leaf that made to float in water. Since it is free to move, then since it is floating, the leaf that is floating, and on top of it is a stone, then it can orient itself to point a particular kind of direction. Now, there are materials, ladies and gentlemen, that are basically attracted to magnets, and these materials are obviously called ferromagnetic. So the word ferro or Fe is iron basically, and a lot of its derivatives. So materials that contains iron basically are the ones that are strongly attracted to magnetic fields. So other materials that do not react or probably less affected or very, very remotely affected are the diamagnetic materials or the paramagnetic materials. They don't respond whenever you put a strong magnet in these materials. So like for example aluminum. Look at aluminum. Aluminum will never react at all when you put a magnet near it. But again, those with iron base, so there's iron in it, will immediately be attracted by the magnet. Now, steel is a alloy. It's an alloy that is containing some amounts of iron in it. So you can make it stainless. Stainless steel is containing iron, but it does not corrode immediately. Now, iron in itself is easy immediately. It can immediately corrode. But you can combine it with another metal and create an alloy of steel that is much more stronger and more elastic. So steel is used as a spring. Very, very strong spring. Like in the suspensions of cars, the one that they call a shock absorber. There sometimes there are springs there, in the suspensions of cars, so that's the one that will absorb the movement of the car, so that's containing iron, so steel is attracted to magnetic materials, so not all types of materials can be made into magnetic materials. Only materials that contains a lot of iron. So we term them as ferromagnetic materials. Now, materials that can also permit some amounts of magnetism, or it can absorb some amounts of magnetism, are called permeable, magnetically permeable materials. So permeability is one characteristic that you can check whether a material can be magnetized or not. So can it allow magnetism to get in through the material? Now, other than permeability, where magnetism can be introduced to the material, magnetism has to remain also, no? And that's another property of a material of retentivity, no? Some materials can absorb probably magnetism, but it cannot hold the magnetism inside, no? So on a very, very short period of time, it can be magnetic, but after, no, a few seconds, after a few minutes, then everything is gone, no? Now you'll notice that if you have a screwdriver, no, an iron or a steel, no, screwdriver, you can convert it from non-magnetic material into magnetic material, no? Now, a screwdriver that can hold a tiny screw on its tip is, I believe, no, very, very useful. Especially, no, if you are trying to fasten together a very small gadget and you're holding a very tiny screw. Now, the ability of that screwdriver to hold in place, no, the screw, no, will give, no, the technician ease, no, like for example, you are trying to fasten a very tiny portion of a watch, no, a relo, no. So there are components in that watch, and you're trying to put them back, no. So it's very advantageous if the screwdriver or the tool that you are using can lightly or carry, no, those very tiny things, no, rather than you hold it with your finger, no. So retentivity is one type of one property, you know, that allows you to know whether the magnetism you introduce in a material can remain, no, or not, no. So both of these are needed, no, in making a material magnetic or not, no. Now, magnets, no, magnets are used on the doors of this refrigerator, but more than the door, you see that in the motor behind, no, the refrigerator, you use actually a magnet there, no? For the components there to spin, no, in your refrigerator motor, it has to contain some kind of a magnet there, no? Now, when you notice that when you when you are using your refrigerator, there's a humming sound, no? Especially if it is working, if its motor is working, because that motor is actually spinning inside, no? Now, the one that causes the motion there is some sort, no, of an effect called a catapult effect, no, which is a result when some versions of magnets are activated. So the catapult effect will create a force, and that force is made to be there, no, constantly. So some things will now eventually rotate, no? Now, you notice motors today are so powerful, no? We have electric cars that are so that can run, no, in a matter of 0 to a few seconds, no, and it can reach its top speed immediately, depending on how you, of course, no, require it to reach that speed, no. So therefore, in this day and age, no, the advancement in the creation of motors is so effective, is so efficient, that people, no, can be in a car, and that car can bring them, no, just about anywhere, and can travel very, very fast as well, no, because of these powerful motors in the car, no. So you may not use anymore fossil fuel or crude oil, no, and you can just simply charge your car, no, because of the advances in this electric cars nowadays, no. And again, the one that is responsible in making those cars run are powerful magnets, no. So magnets definitely have some usefulness, no. Now, we see that in a bar magnet, no, there's always two poles, no. One is the north, and then the other one is the south pole. Now, sometimes if you have a bar magnet like this, one of the poles are colored differently, like green or red, no. And again, one is marked, no, as north, and then the other one as south, no? Now, if you have a single bar magnet, what you will notice is that on its poles, no, comes magnetic lines of force or magnetic field, no. Now, usually the strength of the magnetic field or the magnetic lines of force are many or considerably, no, the density of the magnetic field, no, is more concentrated on the poles, no. Mas damo na di ang lines nga nagaagi on the poles rather than on the side of the magnet. So if you want to get, no, the strength, no, or use the magnet, no, on its maximum, then you have to look at the poles of the magnet. So we call that strength of the magnet, no, on its ends as the magnetic flux density, no, or no, I think, no, the magnetic induction, no? And usually, no, they symbolize that with letter B, and it has a unit Tesla, no. So how strong is the magnetic field, no, or the magnetic field strength, no. So Tesla again is a guy, no, and we use his family name, no, as a unit of magnetic field strength, no? So where is the concentration of this magnetic field strength? Again, no, on the ends of the magnet, no, on the poles, no. Now, some misconceptions: all metals are magnetic materials. We understand that it's not true, no. Okay, so ferromagnetic materials are the ones that we can attract, no, and we can also convert into a magnetic material, no. So again, no, there are magnets that are naturally occurring, like a lodestone, like the earth, no, but there are also magnets that we can prepare in the lab. So naturally occurring and those that are, no, artificially, no, made, no. So man can have, no, his own magnet, no. You can make it, no, more effective, like the ones that we build for cars, no, the one that we build for motors, no. So so not all materials, however, can be magnetized, no. There are diamagnetic materials and paramagnetic materials. And again, no, and other, no, misconceptions there, no? So can we split the poles, no, of our magnet, no? So the answer is no, no. If you try to cut the magnet in half, trying to think that if you cut it at the middle, that the north and the south poles can now be separated, then now we will simply end up with another, no, two sets of magnets, no. If you cut the magnet, one single bar magnet, you cut it in half, you'll end up with two bar magnets now, smaller in length, but both with north and with south poles, no. So the poles there comes in a pair, no? Not like a charge that there's a separate positive charge and then there's a separate negative charge, no? Not for magnets, however, no? So a permanent magnet can be split into two or more magnets, no? But each of them will have a separate north and south poles, no? And you could not isolate or, no, separate the two, no? Up to I say, no, I think now they said up to a microscopic level, no? Now, what makes this north and south poles, no, impossible to split? Or maybe, no, how can we also make one metal magnetic and then the other one not magnetic, no? So perhaps now when they start to create the screwdriver used, no, by technicians that pick, no, very tiny screws, no, in their work, that screwdriver did not just become magnetic, no, immediately. At the very start, after it was created, probably it was not magnetic, no. So what did they do, no, to make it magnetic after some time, no? Now it has to do about this magnetic domain. So the magnetic domains are something like these arrows, no, that are pointed, no, at the very beginning in a random way, no? So look at the magnetic domains, no? Some of them are pointing down, some of them are pointing up, some are pointing right, some are pointing left. So if they are disorganized in this way, you could never expect that the material here, no, well, even though it is ferromagnetic material, that this material will not, no, become magnetic at all, no? Now, the only way that you can make it magnetic is to convert its randomly pointed domains or magnetic domains and make them align in such a way that somehow they can be arranged in such a way that they will now have a something like a direction from left to right. So from the second diagram compared to the one above is simply a very very random way of putting the magnetic domains. But the question is, how do we change state from this randomly pointing magnetic domains into something like nga daw nag-align na sila, something that they are now able to point from left to right. Is it possible for these domains that are actually so scattered, muskin diin lang sila nag-point, and then make them in such a way that they will now align themselves. Now, there's a process of making these microscopic materials, microscopic structures, to realign. And again, that is by introducing energy. We understand that electrons, or molecular particles, will now increase their activity when you introduce some kind of energy. Like, for example, you heat it up. If you heat up the material, then they will now vibrate. Now, the vibration of the materials here will somehow cause them to have a chance to realign. Now, if you put it in between two strong magnets, like you align this to the magnetic field of the Earth, then now all the north pole or this pointed arrow will now position themselves pointing in the direction of our Earth, aligning themselves to the magnetic field of the Earth. But of course, you have to introduce heat. Either heat or you hammer it. The atoms there will have a shock if you hammer them, and then therefore they would have a chance to realign. So from the top, from a demagnetized state, little by little, these domains can now realign and make themselves magnetic. So once all of them are now looking like this below, then now maybe you can have a clear north and south pole in this metal. And once they are behaving in one north direction and one south direction, all of them in that fashion, then you could now have a magnetic material. So, but again, some methods of doing that is by stroking. You provide some kind of a shock and you stroke it by a magnet. So stroking will also produce some kind of a heat, but the stroking method or the rubbing method has to be done in one direction. You could not do it anywhere like that, but little by little you repeat the process and only do it in one particular fashion. So you could not do it and rub it in any manner that you want. Just like in hammering. If you will hammer, then you hammer from left to right. And then you put the magnet in between two strong magnets. Now, in that way, as you hammer, then you let the particles inside to move little by little because of the shock that it receives from hammering. Or again, aligning it with the magnetic field of the Earth. Now, one common method also is by placing it inside a coil of wire, a coil that carries current. Now, that method will now cause the magnetic field to be created and set up, and then therefore you will now have a magnetic substance. So these are our methods of magnetizing or demagnetizing. Now, banging or hammering again could make the material non-magnetic also, especially if you hammer it in any direction at all. But if it is not magnetic and you hammer it in only one direction, you can also achieve a way of making it magnetic little by little. So magnetic induction, no? If you have a permanent magnet, this permanent magnet above, no, can induce temporary magnetism on this paper clip, no? And the paper clip can now become, no, a magnetic material, no, because maybe it's permeable, no? It can permit magnetism to go in it, and then therefore, no, attract other paper clips, no. But perhaps now after the fourth one, no, maybe it's not strong enough, no. Then maybe the paper clip already fell, no. So again, no, this is known as your magnetic induction, no? This temporary magnetism that we now create, no, on the paper clip. Now for our straight wire, guys, no, so the wire, when you put, no, a current into this rod or wire, no, that passes through some kind of a paper, the wire there, no, since it moves, no, a current, no, from the bottom going up, no, then there is a magnetic field that will be around the wire, no. Now this magnetic field, no, is this magnetic field, excuse me. Now again, in predicting the direction, no, of the magnetic field, we use our right hand. The right hand, where the thumb and the forefingers, no, are grabbing, no, this wire that carries current from the bottom going up. So if the wire is carrying current going up, the behavior of the magnetic field will be in a counterclockwise direction as pointed by the other four fingers of the right hand, no? So this guy again, no, is grabbing this by his right hand, no? So if you grab the wire that carries current, no, a straight wire, and then the thumb pointing to the direction of the current, the other four fingers determines the direction of the magnetic field or the, no, magnetic lines of force. Now this magnetic lines of force does not have a beginning, it does not have an end, no, but it is spinning round about the wire, no, so long as the wire is allowing current to move, no, from the bottom going up. Question: what if the current goes from top going down? Then maybe, no, by using your right hand rule still, you'll notice that the magnetic lines will now move clockwise. It will now move clockwise, no? So again, how do you know exactly where is this direction, no, or this rotation? Does it really exist? You can either pour some iron filings to visualize, no, the path of the magnetic field, no? If you want also, you can use a compass, no, to know, no, the changing nature of the magnetic lines of force on the sides, no? So again, we use the right hand rule principle there, no, to determine, no, the value of our, no, magnetic lines of force. Okay, now we go to another kind of a wire now, but this time the wire that we will have is some kind of coiled, no? So you loop around a wire and you can give it several turns, no, and you can end up with a coil of wire, no? So there are two ends there of the coil that you can probably use, not to connect it to an outlet or to a battery. Now, if you stretch this coil of wire and make it into a spring-like arrangement, no, so you'll have a helical spring here, no, that does not have, maybe, no, it's continuously winding because you stretch a coil. Then you can let current pass through one end of the coil of wire, no? Now that coil of wire eventually, no, will now let current be moving on this coil. And because of that moving current in the coil here, which we call as a solenoid, it will create a magnetic field inside, no? One end of the coil, no, will become the North Pole, and then another end can be considered as a South Pole, no? It's as if you inserted something like a magnet inside, no? But actually, no, there is no magnet created in this solenoid. All that you do is to simply create a coil that you stretch and you let that coil, no, you allow current to pass through that coil, no? So again, no, the current will be looping around, no, and then coming out on the other end and go down, no? Okay, now the way or the behavior of the current as it goes into this loop, no, could probably no be determined ang iya direction with the use of your right hand still, no. So using the RHR, the right hand rule, no. So if you will grab the coil, no, the solenoid, no, directly, if you grab it directly, just like what this guy is doing, now your fingers, no, pointing to how the current is going around, no, in the coil, no. So your four fingers will determine how the current is going about the coil, no? Will now tell you, no, that your right hand, no, your right thumb, no, the thumb will point to the direction of the North Pole. No? So earlier, no, in a straight wire, the thumb is used as the direction of the current. But if it is a solenoid, the four fingers will be used as the direction of the current. And then as the current is determined, its direction is determined. No? Then therefore, no, as it passes around the coil there on the solenoid, the thumb will point to the direction of the magnetic field. So if this is now the left side, if the left side is now the North Pole, then it will now go into this kind of a loop where the other right side end is now the South Pole. No? So similarly, no, even though there is no bar magnet that we see, the solenoid on this right side, no, behave like, no, the one that you see on the left, which is a bar magnet. No? So there seems to be an imaginary North Pole here. If you let this coil of wire, no, or solenoid, you let current pass through this solenoid. No? Okay. So again, no, as the current is going roundabout, you notice that on this side facing you, all the currents there are going up. No? So as the current goes up, the thumb will point not to your left. No? So the left will now become your North Pole. No? So the right hand rule. No? So here is another image, no, of how the right hand rule can be applied, no, in a straight wire. No? So whether the current goes down the wire, then you will know what is the direction of the magnetic field by looking at the four, no, curled fingers. No? So that is for a straight wire. No? So the fingers are for the magnetic field. The thumb is for the current, no, if you are dealing with a straight wire. No? If it's a solenoid again, the current will be the four fingers, and then the thumb is the direction, no, of your magnetic field. No? So north kung solenoid siya. No? So ang north is the direction of the thumb. No? Now, looking at this, no, so we see that we grab the wire, no, and the current in this wire is going up. Now, if the left side here, no, a dot is being shown. If that dot, no, is the direction of the magnetic field that goes towards you, no. This X portion on the right side, no, is where the magnetic field enters, no. So X is where the magnetic field gets into, and then that there is where the magnetic field goes out. That it will seemingly appear that the direction of the magnetic field in this case is counterclockwise. No? So if you look at it at the top, it seems like it is moving, no, in a counterclockwise manner. No? So some notations are showing, no, the dot and the X. No? So the dot may probably mean, no, coming out, and then X is when it is getting into, no, the board, no, or into this flat screen. No? So the current will eventually go upward. Now, usefulness of motors, we have of magnets. We use it in motors, compass, in storage devices like magnetic discs, magnetic tapes, no? And in imaging, no? In MRI, we also use the magnetic property. No? So I think, no, imaging like X-rays, no, like MRI, CT scan, allows us to diagnose or allows doctors to diagnose a patient without necessarily, no, slicing or opening them up. No? So what if no, in the old days where they want to know no, what's happening inside you, they have to slice you open first, no, and check your organ before they can say, oh, okay, so you are not, you're actually fine, no? So you are fine, but you've been cut already, no? So again, to avoid creating an injury, no, so they have other ways and means, no, that is non-invasive, no? So they call it as a term, no, non-invasive, when they don't have to, no, introduce something towards your body, no. So they can probably do X-rays, no, and other imaging tools, no, to know and to identify, no, whether you are really sick, no, or where is that sickness coming from, no. Okay, so we've talked about motors. So today's motors, no, we use it in cars, no. Our cars could go, no, so large. I've seen some mobile homes, no, that are actually no electric in nature, no. So they can charge their mobile homes, no. And again, no, they can get very, very large, no. So from very tiny motors where you can fly, you know, a drone. So in today's technology, no, we have a lot of drones created today that can fly very, very fast, no. So what makes it fly so fast, no, or so high? Maybe it's because of the motors that are built in that are so light but are so powerful, no? So they have a very, very high magnetic property, no, that it can spin so fast, no. Now the hard disks, if hard disks are still used, no, they can increase it to several gigabytes, no, or maybe even terabytes, because again, no, it can spin so fast this time, no. So the spinning ability of motors, no, has provided a way of storage, no, to increase, no, the amount of storage, no, storage of data in computers, no. Loudspeaker is also another useful way of applying your uh, magnetism, no. Microphones, the buzzer, no. So the buzzer is a device that will cause, no, something like a hammer to strike a bell, no, because of the magnetic property that is being activated, no, whenever you turn on the buzzer, no. So instead of doing it, no, manually, there's a hammer there that is maybe kind of small, but can strike, no, the bell, no, several times, no. So the usefulness, no, of motors, no, or electromagnetism. Now, what makes the motor move? We have this catapult effect, na? This force that causes the wire to swing. Now, why will a wire swing? Now, there are three things that are present, no, in order for a wire to swing, or maybe not two. So one is the magnetic field. And you'll notice here that we have a separate, it seems that there's a separate north and south pole here. No? So maybe, it is actually, one of the face or poles, no, of two separate magnets. You can do that. No? You can brought them together, the opposite sides of that magnet, or you can bend one bar magnet and shape it like letter U. Now, shaping it like letter U can make you, put the two poles near each other, no, rather than on one long bar. No? Now, if you try to bend it, no, then you can make the poles there come closer. No? Now, the magnetic lines of force are actually coming from north to south. No? So this is the direction of the magnetic lines, no, from left to right. No? Now, if you put a wire, no, in between, no, this, if you put a wire, no, in between and let that wire, no, run with current, no. So this is a straight wire, no, that is in between, and since this is a dot, then maybe, the current is getting into, no, it is getting into or getting out. I mean, getting out of the board, no, or the screen, no. So the dot is when the current is going out of the screen. No? Now, if you look at the diagram on the far lower right, no, there's a left hand there that is being shown with 3 fingers that are in perpendicular direction each. No? Now, if you look at the forefinger, no, the pointing finger, which is a forefinger, is named as field. No? Now, the field in this case is from the north to the south, which is from left to right. No? Just like the pointing finger that is also pointing from left to right. No? Now, the current, if it is coming out, no, of the screen, no, because this straight wire, no, is carrying current, you put this in a battery, and then the current therefore is going out, no, just like this center finger of the person. No? So center finger C is representing the current. No? So if it is coming out and going towards you, no, and the field is moving from left to right, no, using your left hand, no, look at your left hand. No? Now, the other finger, the thumb, no, will now represent the thrust. The thumb is for the thrust or the force. No? So the force will be upward, and the wire that carries current will now swing up. No? So where did that force come from? Again, it's because of the field, no, interacting with the current, no, in the wire, and therefore it results to a force. We call this as the catapult effect. No? So every time the wire is being energized, it will have a swinging effect. No? Now, if you put it inside a motor and have a continuous amount of current go through the wire, then you can make, no, a series of motion that will be continuous. No? So if you position wires there, no, in such a way that when one of them move, no, the other one will also move. No? Then eventually, if all of them are being activated, then you will create a spinning rotation. No? So you can create a torque, no, in that case. No? And the torque, no, if it is imbalanced, will keep on spinning. No? So that's what we see with electric fans and many other electric motors, no, which we find very useful. No? Pumping water, no, and making yourself cool, no, using an electric fan are very, very useful and practical use of magnetism. No? Okay, this is a motor. And again, a motor will need a wire that carries current. It will need a magnet or magnetic field. No? So the magnetic field is from the north going south. And if this wire again is carrying a current, no, from the positive end, no, to the negative end, then therefore, no, this motor will now rotate. No? And again, no, look at how it rotates. It rotates from clockwise, no, manner. No? So it's rotating in a clockwise manner. No? Again, no, you can know that direction, no, by looking at the flow of the current. No? Loudspeakers, no, since speakers are moving, it creates, no, some motion there. Then sound can be produced, no, mimicking your voice. No? So it can mimic your voice or anybody else, no, because the speaker is actually, no, moving. No? So as it compresses, no, it will find that frequency that will match your voice. No? That is if you record and you play it, no, and you let the speaker interpret what was said. So a speaker is very, very useful, no, tool, no, in its day, no, or right now. No? Now, wires that carries current, no, in the same direction, no, like this one. No? So the picture on the left, these are dots, and these dots are carrying current towards me, no, or towards you, no, looking at them. No? Now, if it is moving towards you, then the tendency of the wire, no, if they move in the same direction, is that for them to now draw and stick with each other. No? So the resulting force when you let currents move towards you or in the same direction is that there's a possibility that the wires will now, no, stick with each other. No? And maybe, no, you can create fire or short circuit, no, if the wires will force themselves, no, to be together. No? But if you let the wire move in two opposite direction, so this one is negative force. This is your so this is this is a wire that carries current outside, going towards you. This one X is a current that is going into the screen, and then therefore if it goes into the screen, you can grab it using your right hand and you use right hand rule, and you can predict that on the left side here it will be clockwise. However, if it is going out, you grab the wire and it is going out, then you'll notice that it will be clockwise in this other end. So the two directions are opposite one another, then therefore they will kind of repel. So they will not help one another anyway. Okay, generator is another way of applying our magnetism. So this one is producing current. So the bulb will glow there because the wire is now carrying current, because you let a wire pass through a magnetic field. So that's how generators are actually made. Okay, another function of these coils of wire and the magnetism is when you step down or lower down a voltage. So if the voltage here is so high, so for example, it's 440 volts, you need a transformer to lower down the voltage and make it usable in the homes, make it 220. But again, you have to put a transformer, okay, so you can maintain such good condition of the you must have this transformer here, so you can step down or lower down the voltage. Okay, magnets, when you place them side by side, will eventually either attract or repel. That's the basic law of magnetism. So when you let two poles come together, then they will attract one another. So they are basically having two poles each. Each of them will always have two poles. So it's not possible again to separate the north from the south pole. So this is how the north and south pole again behaved. So we call these lines as magnetic lines of force or magnetic field. So there's a region here somewhere in space that you could no longer feel this magnetic field. So again, the magnetic field does not terminate. As it comes out of the north, it will get to the south, but it enters the magnet and makes it complete path. Okay, so again, so we have here our magnetic lines. And again, the magnetic lines does not end when it reaches the south pole, but it enters the magnet and makes one complete rotation or loop. Okay, so a magnet that is if you bring a magnet, then they will align themselves depending on how strong is the magnetic field where you place them. So but anyway, the south pole of that magnet will always be attracted to the north pole of the second magnet. Okay, so again, here is a wire and you place it in a battery. So again, we do not use this or we do not make this in real life because you will get burned if you do it like this, connecting the wire directly to the battery. Now, a compass will behave, no, depending on how you place it in the wire here. No? So if you put it side by side in the wire, then the compass now will, no, behave as though there's a magnet that you place it with. No? But actually, no, there's none. No? There's no magnet. It's simply a wire that carries current. But your compass here, no, will behave as though, no, it is placed side by side to a naturally occurring magnet or to an artificially made nga magnet. No? But again, there's none here because this is simply a wire with a current. And this one shows us that a current carrying wire will produce magnetic field. No? Okay, so this is our wire. Around it, no, there are magnetic fields, no, that is going around. And maybe, no, if the current is going into, no, so it is going into, so the magnetic field or the magnetic field strength is going, no, in a counterclockwise direction also, no? Counterclockwise ng your direction. No? I don't know, it is in a in a clockwise direction. No? Okay, do you have a question? So again, continuing to our discussion, we mentioned about the right-hand rule a while ago. And how about the planet Earth? Now, the planet Earth, again, is a naturally occurring magnet. So this is a this is one huge magnet. No? And what's the significance of the magnetic field of the Earth? I think now the Earth's magnetic field shields us now overall from the harmful radiation from the sun. There's this radiation that is created, no, solar wind, as I think, no, that's what they call it. So there are instances when this solar radiation from the sun are so strong after these solar flares, no, erupt in the sun, no, and then in a matter of what, no, a short period of time, they will reach the Earth. And if there's no magnetic field that covers the Earth, no, or shields the Earth, then probably, no, all of us will die. No. Uh, so again, no, so some usefulness of this magnetic field that shields the Earth. No? But as a huge, no, compass, or as a huge magnet, then naturally, no, the compass of the needle, no, the north portion of the needle of the compass will point north, not to the north, to the true north of the Earth, because we call that part of the magnet or the compass as the north-seeking pole. No? So maybe, no, one of them is actually, no, a south pole in reality. So it could not be that north and north will attract. No? So that violates the basic law of magnetism. So in reality, one of them should be a south pole. No? So that is for attraction to occur. No? Now again, now what is inside the Earth, no, that makes it somehow, no, produce magnetism? This liquid portion of the Earth's core, no, the liquid metal, no, that is going around, no, in the Earth's core. So I think, no, that's the outer core, is the one that causes, no, the magnetism to, no, to be created in the Earth. No? So if they say, no, if this motion inside the Earth's core will stop moving, then maybe, no, the magnetism also will stop. No? Now, also the question about gravity. No? So gravity and magnetism are two different things. So gravity, I think, no, is with regards to the size of the planet. No? And however, no, the magnetism may probably, no, be due to, no, the spinning motion. No? So I think, no, in Venus, no, there's less magnetic field in Venus, because I think, no, it spins also rather slowly. No? So look at Venus; it's so beautiful from a from our vantage point. No? But actually, no, Venus is not a safe planet to stay or live on. No? It is filled with um, plasma gases, no, and again, no, nobody can survive, no, in the surface of Venus because of its hot temperature and all this, no, harmful radiation in Venus. So again, no, the one that probably, no, is responsible in the magnetic field of the Earth. No? So the molten iron core exists, no, in a magnetic field that had been created, no, from other sources. So the fluid is rotating in this field. No? So this motion causes a current, no, in the molten metal. The current causes a magnetic field. The process is self-sustaining. No? So I don't know if that motion in the Earth's core will stop moving, then maybe, no, we will have to have, no, a that magnetic field will eventually also stop. No? So in ancient navigation, they use the compass, no, to navigate, and they are able to locate their where they want to go. No, not like when you simply rely on celestial bodies like a star, no, at night, and if it is there's a storm, no, or it's being, no, a bad weather for several weeks, no, then you will get lost, no, in navigating. No, so but not probably this one. No? So if the Earth is aligned, no, and then there's a magnetic north and south pole, then maybe, no, we can use the compass, no, to align and know where we are in the planet, no, because of the magnetic nature of the Earth. No? So we can use the Earth, no, as a tool, no, to navigate where we want to go also. No? However, it's not a perfect angle because, no, there's what they call a declination. I think, no, the word here is a magnetic declination. That in every locality and in every area on the Earth, no, there's always this number of degrees that you have to consider and correct, no, your direction. So this magnetic declination, you have to adjust, no, your compass, no, with this number of degrees, so that you can use effectively the compass and not get lost also. No? So if you will simply rely that the angle or the direction where it is pointing is the correct direction, then maybe, no, you have not considered the correction angle there. No? So again, no, from the true north and the magnetic north, no, there's a difference there, no, that you have to consider. No? So you have to know that if you are to use, no, your compass as a navigation tool. And again, no, from place to place, that angle is also, no, different. Now the magnetic field, no, the magnetic field strength of the Earth, no, is 3 times 10 to the minus 5 Tesla. No? This is the surface of the Earth. No? Our magnet, no, is 5 times 10 to minus 3. It's a bit stronger. No? Lab magnets is 0.1. No? That's quite strong. But some superconducting magnets, no, superconductor magnets, they kind of levitate, no, when you put it in a superconductor. No? That's 10 Tesla. No? So that's very, very strong. No? That's something like 100 times more than a laboratory magnet. No? So you can actually kind of move a magnetic a charge, no, in the presence of a magnetic field. No? Again, maybe because of the laboratory settings there. No? So they are using some very, very powerful magnets, no, in the lab. No? Now, for our wires, no, some wires that carries current, no, will either repel or attract each other, no, depending on the direction of the, no, the current in the wire. No? So if the currents are probably moving in some way, no, then they would tend to, no, pull each other towards each other. No? So the wires will be attracted to one another. No? Now, some applications of the magnets, no, in trains, no, or in electric trains. So of course, no, the trains that uh, uses magnets, no. So they have this maglev or magnetic levitation. No? So maglev, no, they will levitate the train, so there would be no friction on the tracks of the train. So when there's less friction involved, then you can make the trains travel quite fast, no, because of the no, they were able to minimize no the effect of friction. No? So brakes, no, make it levitate, no, then naturally, no, you can travel from one point to the next, no, using this levitation principle. No? Now, when same poles of the magnet are facing one another, then there will be repulsion. No? If the magnets are are that strong, no, then you know, even though it's placed in a train, still no, they will tend to repel one another. No? So maybe now the kind of magnet that they have there is what? Is an electromagnet where they can change the poles of the magnet. No? So they can reverse the whether to make it attract one another or to repel one another. No? So something that they do no with the magnets where they can reverse no and make them contact and no sometimes no make them repel one another. No. So maybe now this is how they make the levitation principle. No. Now if we will let no the train move, then maybe no they will also apply that same technique of attraction and repulsion. No? So if the north and north repels one another, then the train will be propelled to move forward. No? So again, no, if you make this a track, then as this one no, reaches this point, then it will now tend to move forward. No? So maybe no, they have a way of changing no this poles here no, so that this one will continue on its way. No? So making no the principles of repulsion and attraction no, efficient in such a way that it can even no, move a huge object like a train no, with people and things no, and cargoes inside it no move. No? So again, no, this is the last one, and maybe this is one application that we will end with no on the use of magnets. So we learn how magnets are used. We can store data no as a kind of a magnetic storage. We can use it to produce sound no like in a loudspeaker. We can use it for motors no to pump water to make our refrigerators work no make it cold no and so on. No? So the usefulness no of magnets no. And not only in motors but even in producing electricity just like in generators no. So we use also the concept of magnetism in that area no. I think no I it's worth mentioning also about the transformers that steps down voltages no from a high voltage to a low voltage so that we can use them are also worth noting no for this morning. No? So that's our discussion no, on magnetism. No? Unless you have a question. Questions related to our lecture? If there's none, however, we can dismiss the class. No? So see you guys next meeting.
Thank you, sir. Goodbye, sir.